this problem solving. Then how to identify the square, all the squares. I want to say there is an easy way. Use horizontal lines and vertical lines. That will be pretty easy. Okay? Yeah. For each square, so here, yeah, let me use one, typical square somewhere. Yeah. Because there are 4 sides, each square, 4 sides. Yeah. Then we look at the orientation. Yeah. 2 parallel sides in the horizontal orientation, right? Yeah. So here I use this, 4 by 4. 1, 2, 3, 4. 1, 2, 3, 4. All right. This 2 horizontal lines, yeah, along the grids. Yeah. Then 2 vertical lines along the grids. Okay. These 4 lines can help us determine one particular square. That's the simple way to identify a square. So for all the square with different sizes, we can use this way. Yeah. So here we only need to use 2 horizontal lines and 2 vertical lines. Okay. How many horizontal lines do we have? Counting, how many horizontal lines? Is it 8? Is it 8? Let's count, okay? All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 9 horizontal lines and then 9 vertical lines. Okay? Along the grids. Okay? All right. So we use these lines to help us do the counting. Counting number of squares of different sizes. Yeah. All right. Then, next step, the critical step, how to manipulate the data efficiently. So in our problem solving, there is this question. Yeah. Because if the data given is like this, here, at the beginning, it's pretty messy, right? So the data distributed in some random way. Yeah. So the first thing, so one important step you need to do. So here I call this critical step. Arrange the data in a well-organized way. Yeah. Yeah. So if you do not organize it well, pretty messy, then when you do the counting, you get lost. How do you keep track of your data? Right? Yeah. So you need to find a well-organized way to put your data in different categories. Different categories. Yeah. Then you do the countings in each category. If all your data belongs to many categories, and when you do the counting on your data in all those categories mixed together, it's hard, right? Yeah. So many different categories. When you do the counting, you need to, some squares in this category, some square in other different categories. Then it's hard to keep track of your data. So here we need to use the good categories to organize the data. All right. How to organize the data, characterize the data in suitable categories. Yeah. So what are the suitable categories here? Think about that. Suitable categories. Based on the sizes, right? Yeah, here. The size information is important. Size information. Yeah. All right. So that the data in the same category shares the same property. Yeah. So that's in problem solving. So this step is important. Why we organize our data? This is the reason. Okay? Because after we organize our data in suitable categories, then in different categories we apply different properties. Then it's much easier. Otherwise, if you do not use those categories, you mix the data from all different categories, you cannot keep track of your data well. All right? Now here, what are the category squares of these sizes? 1 by 1, 2 by 2, all the way through 8 by 8. So we have 8 different categories. That's the way we use to organize our data. We organize our data in these 8 different categories. Okay? Yeah. So this step, one important step in problem solving. Right? Main work here, we need to do the counting. So far, what we are doing so far, that's the understanding part, right? Yeah, so yes, you can see we spend so much time. Yeah. That's useful. Yeah. The time we spend, not wasted, because we understand our problem better. Okay, much better. Yeah. Now we are ready to do the counting. Yeah. After we went through, a lot of mental work, right? A lot of mental work in understanding. So now we feel we are ready to do the counting. Okay? All right? Yeah. Let's do the counting. Squares in various sizes. Okay? Yeah. In 8 different categories. Size, we have these 8 different sizes. Yeah. So 8 different categories. Now let's do the count. In each size, each category. Now, when you do the counting, we only need to look at the number of squares in each of the 8 sizes. Yeah. When we count the number of 1 by 1 squares do we have? Only 1 by 1. Okay? Don't look at other squares. Only 1 by 1 squares. How many? $64. Correct. 64. Right? 64. All right. How many 8 by 8 squares? 8 by 8. 1. Yeah. These two easiest. Then between, yeah. The other categories between. Now, a little harder. Now I ask you, how many 2 by 2 squares? 2 by 2 squares. This one, a little harder. Yeah. Anyone can see 2 by 2 squares? 2 by 2 squares. How to keep track of the squares, right? Yeah. Very easy to get lost. Yeah? Okay? Very easy to get lost. Yeah. All right. So here, let me use a way that can help us keep track of the data. Yeah. So if you use the right way, then you can do better. You won't get lost. Okay? All right. We know when we do the counting, each square the four sides of each square, we look at the horizontal two sides and the vertical two sides, right? Yeah, remember, how do we identify a square? Two horizontal sides, two vertical sides. Let us use that information to do the counting. Okay? Horizontal, vertical, we separate. Let's separate horizontal sides and vertical sides. Yeah, we know they are together, but so here, when we view this question, we need to, so here, do our mental work. We can separate these two different types of sides. All right, so let's just look at the horizontal sides. We forget about the vertical sides, only horizontal sides, okay? Horizontal sides, yeah, because for 2 by 2, horizontal side, we only need to look at the length 2 segment that is used to form a 2 by 2 square horizontally. Yeah, length 2 line segment. How many length 2? How many different length 2 line segments horizontally? Okay, all right? Yeah. 1, right? Yeah, the first one. Okay, all right. Then when we do the length 2, it is legal we use this length 2, horizontal side. Okay? Yeah? Okay? Yeah. All right. Then another one, length 2, another one, then all the possible length 2 horizontal sides we can use. Here. Okay? Right. 1, 2, 3, 4, 5, 6, 7. There are 7 length 2 horizontal sides. Here, you do not need to keep them, without overlapping. Yeah, some students, so they told me there are 4 horizontal sides because they arranged these 4 sides without any overlapping. They do not feel comfortable, but here we allow overlapping. Why? Because the first time we use this horizontal, length 2 horizontal sides. Second time we can use this, yeah, because when you use this, you can form squares like that, right? It's legal. You can use, that kind of length 2 sides, right? It's legal, yeah. So things like that. So that's why we can do it this way. 7, right? Then, when we move to the vertical sides, how many length 2 vertical sides? Length 2 vertical sides.
Well, it would be the same.
Same, yeah, same. Yeah, here, why same? Why same? Yeah, it's a square. Square has nice property, symmetry property, right? Horizontal, vertical, can you view it with symmetry? Symmetry, right? Yeah, so in our problem solving, many times we need to use the symmetry properties. Okay, symmetry properties. Okay, so here, also 7. So horizontally, you have 7 different length 2 sides. Vertically, you also have 7 to total number. You can do multiplication. Okay, 7 by 7. That's how you get 7 by 7. Yeah. Because in that way, you won't get lost, right? Yeah, you won't get lost. But if you count the 7 by 7, 49 directly, you may get lost, right? Yeah, it's hard to keep track of it. But when you separate horizontal sides, vertical sides, they're much easier to keep track of your data, right? Yeah. So use the right way to help you keep track of your data. Okay, all right. Then, can you tell me how many 3x3 squares? Based on our experience, at this point we build up a lot of experience. So based on our experience so far, can you predict?
6.
Yeah, 6 by 6. Reasonable prediction, right? 6 by 6. All right. So, yeah, 6 by 6. How about how many 4 by 4 squares? Induction. Yeah, that's induction, right? Yeah, because you observe the rule. Yeah, you find the rule. Yeah, many of you at this point, you discover the rule, right? Yeah, 5 by 5, 4 by 4, and so on. Okay, all right. Now, the last step, how many number of squares? Add up all these numbers, right? Yeah, add up all these numbers. You get an answer. Yeah. So here, let's look at the rule. What is the rule? We need to summarize to find that rule. Yeah. So here, yeah, 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 because you use induction to help you. By the induction, you do not really need to every time you count explicitly, right? Yeah, you can save a lot of work by induction. Yeah. So here, what is that rule? We need to summarize. Okay? Yeah. That rule, yeah, here, let me give it to you. All right, all right. Can you see? So if 1 by 1, we just take 1. Here, A by A, we just take 8. 1 plus 8 equals 9. Okay? 2 here, 7 here. 2 plus 7 equals also 9. Okay? All right. So for each line, we take the size number. Okay? Yeah. Adding together, it's a fixed number, right? It's 9. So for all the rows, that 9 is the same. When you go through all the 8 rows, that constant, we treat that special constant 9, it is fixed for all 8 rows. This property is nice, right? Yeah, this is a nice property. In problem solving, we have a concept for this property. Yeah. Yeah. All right. So let's consider the general case. Yeah. The size number, we use m by m to represent the size. Then the number of squares we write as n by n. Yeah. Then these two numbers, m number and n number, the sum of these two numbers equals 9. M plus n equals 9. Yeah. So this property, we have a concept for it. We call it invariance property. So this concept, we call it invariance property. Yeah. So in problem solving, this invariance property is very important. Yeah. So this property can help us keep track of the data. Yeah. Yeah. We know, so many times if we work on the data directly, it's very easy to get lost. Hard to keep track of the data. We get lost. Okay? Yeah. But if you can discover this invariance property, discover it and use it, then you can keep track of your data much easier. Okay? So here I introduce this concept. Yeah. Later, when we do other problem solving, yeah, sometimes we need to use this invariance property. Yeah. Okay? Yeah. All right. Yeah. Yeah. Yeah, because, yeah, so here, yeah, we know for all the sizes, this number keeps the same. Yeah. All right. Yeah. Then next, I here I want to use a simple example to show you the importance of this concept. All right. Yeah. All right. Understand the role of this invariance. Yeah. All right. Yeah. So here, invariance usually provide critical property, so insight of a problem. Yeah. Usually, it's not easy to discover. Not easy to discover this, invariance property. Yeah. You need to have some very good understanding. Then you need to really to do some creative work to discover the insight. So, yeah. So here this invariance property, that's belong to this insight. Okay. All right. So invariance property can help us keep track of the data. Why it is important? Yeah. Here, let me show you a simple example. How to use the invariance property to keep track of the data. All right. Here, let's consider a generalized chessboard. We know standard chessboard A by A. How about we extend that chessboard? We consider a bigger 100 by 100 chessboard. Okay, just grid. Okay, the grid, squares, unit squares, 100 by 100. So the size much larger, then it's harder to keep track of the data, right? Yeah. If you work on 100 by 100, the generalized chessboard, much harder. Now I want to ask you one question in this larger chess. How many squares are of the size 37 by 37 in this 100 by 100 chessboard? Only 37 by 37. Yeah. I do not need squares of other sizes, only this size number. How many?
64 by 64.
Great. Great. Can other students see that? 64 by 64. Can other students see that? Why 64 by 64?
101 minus 37.
Yes. Invariance property. Invariance in this question, then the side of your chessboard 100 plus 1. Okay? The invariance in our chessboard, the size number 8 plus 1, 9. Here you need to use, because you need to extend your solution from the previous question. This time 100 plus 1, 101. You use that number because m plus n equals 101 minus 37, 64. Think about it. If you do not use this invariance concept, how can you keep track of? It's not easy to keep track of. If you do the mental counting, it's not easy, right? You get lost. If you do the mental counting, how many 37 by 37 square in 100? Yeah. Yeah. So you get an idea. Yeah. Get a point. Yeah. Why this invariance property is important in problem solving. Okay. All right. Yeah. Next. Yeah. All right. So after we see this point, yeah, we need to complete the remaining computation work. Yeah. We need to find the answer. Yeah. The answer, you add up these 8 consecutive square numbers. Yeah. So you can use calculators or doing on the scratch paper. Yeah. Yeah. But here, we can consider the general question. Yeah. If the question is, if we want to count the number of squares in general n by n chessboard, yeah, n by n chessboard, how many squares? Yeah. Yeah. All right. So we do this summation, right? Yeah. N minus squares. Yeah. Because based on, we only need to use our standard chessboard example, yeah, because we summarize the rule. We know the rule. Here, we just apply the rule we observed, we discovered from our first question. We apply it here, so we know it should be this summation. Yeah. For this summation, there is a formula. Here. There is a formula. This is the formula. Okay? Yeah. This is the formula. Yeah. We ask, how do we get this formula, right? Yeah. It's not that easy. Yeah. You can look at, in your discrete math. Yeah. Do you remember if you learned it in your discrete math, Math 3000? In discrete math, you learn the formula 1 plus 2 plus 3, right? This summation formula you learn in the discrete math, right? Yeah. Do you still remember what's that formula? This formula. Simple formula. 1/2 times n plus 1. Okay? Yeah. Then, next one is this. Next one is that one. Okay? Yeah. Then it's much harder. It's much harder. So you need some special trick. Okay? Yeah. You need some, very smart trick to find it. Yeah. All right. So here, I do not go that far. Yeah. Here, I just give you the formula directly. Yeah. Because usually, when people prove this formula, yeah, because if you are given this formula, how do you verify it is correct? By one commonly used method to verify this formula, mathematical induction. By mathematical induction. So that's in your discrete math, right? Mathematical induction. Yeah. Yeah. So later we will have some questions we need to apply mathematical induction. Yeah. All right. Then, 8.2 topic, prime factorization. Yeah. So another topic, prime factorization topic. Yeah. Here, this topic, in our first lecture, 8.2 topic, here I want to prepare for our programming project number 2, our second project. So this prime factorization topic gives us the background for our second project. Okay, yeah. All right. So let's study this topic first. Yeah. All right. Problem number 2, prime factorization. Given a positive integer m, how to represent it as a product of prime numbers? That's the prime factorization problem. We want to write it as a product of a sequence of primes. Okay? That's the prime factorization. Okay? Yeah. All right. And you need to write a program to calculate it. So here, let's look at the algorithm to calculate that prime factorization. Yeah. We need to use the algorithm to write a program. Yeah. So in this topic, we try to find that algorithm to calculate prime factorization. Later, in our second project, you need to write the programs. Okay? So you have a lot of time. Yeah. But here, we do some preparation. Yeah. Right. Yeah. So the reference here, I also give you in our textbook, the section. Very late, okay, 11.3. Yeah. Yeah, because the topic is pretty easy. Prime numbers. Yeah. So you have that knowledge from your middle school, right? Prime numbers. Yeah. So then you have the knowledge to understand this topic. Yeah. All right. Analysis. Yeah. Let's understand the problem. Yeah. First, we want to understand the prime number. What's the definition of prime numbers, right? Yeah. Yeah. Most of you know, yeah, but here let's review a little bit. Definition of prime numbers. Yeah. A prime number is a natural number greater than 1 that has only 2 factors. Yeah. 1 and itself. That's the definition, formal definition of a prime number. First, it must be greater than 1. We do not treat 1 as a prime number, yeah, because 1 is a unit. Okay? 1, we call it, it's a special number. It's a unit number. Okay? So it's a special, it's a unit, so we take it out. Okay? The unit number. After that, then, in the remaining numbers, greater than 1, those integer numbers, yeah, some of them have this property. Each one only has 2 factors. 1. Everyone must have factor 1, right? Itself. Everyone must have itself as another factor, right? Yeah. So here you can see the prime number only has these 2 factors. Other than these 2 factors, no other factors. So that's the definition of the prime number. All right? So we review. Yeah. Yeah. So example, yeah, 2, 3, 5, 7, 11, and so on. Yeah. Okay? Yeah. Yeah. And the prime numbers are very important in number theory. Yeah. So in your district, you have one chapter about number theory, right? The basic knowledge about number theory. Yeah. And these prime numbers, they are the building blocks in number theory. Yeah. So a lot of things rely on the prime numbers. A lot of important theorems rely on the prime numbers. Yeah. All right. Next, composite number. Natural number greater than 1 that is not prime. Yeah, yeah, yeah. Also, yeah, yeah, yeah. Yeah. So for the natural numbers greater than 1, yeah, 1 is the unit, so we take that unit out. Yeah. And look at the remaining natural numbers. Each one either prime number or composite number. If it's not a prime number, then it must be a composite number. Yeah, that's simple. Okay? Yeah. That means if you look at the factors, other than 1 and itself, a composite number should have another factor, at least another factor. Okay? Between 1 and itself for a composite number. Yeah. All right. Yeah. So more than 2 factors. Yeah. Each composite number should have more than 2 factors. Yeah. All right. Example: 4, 6, 8, 9, and so on. Yeah. All right. The question. Yeah. Here, let me ask you a simple question here for the understanding. Yeah. Yeah. Read the question carefully. Is it true that for a given natural number, if it is not a prime, then it must be a composite number? True or false? True or false? Read the statement carefully. Then tell me true or false. Try. In your quiz question, so many quiz questions are like this one. Okay? Check your understanding of a concept. After you learn the definition. False. Why false? Yes. 1. Don't miss that 1. Okay? don't miss that one, unit. Okay, that unit number. Because here, I didn't exclude that unit number. Okay, so that's why I ask you read the question carefully, the question statement carefully. Do not miss any information. Okay, yeah. All right. For a given natural number, how to determine if it is a prime? Now, we really need to solve the problem. Our problem number 2, our computing problem number 2. Now we try to solve it. So this question related to the problem number 2. For a given natural number, how to determine if it is a prime or a composite number? Because 1 is trivial. We do not need to look at a 1. It's trivial. Okay? Yeah. Then, for a natural number greater than 1, now, can you find some way to check, to tell you if it is a prime or a composite number? Yeah. We need to answer this question. All right. Yeah. We need to do factorization. Because the definition tell us we need to use the factor information. How many factors? If it has only 2 factors, then prime. More than 2 factors, composite number, right? Yeah, that information. Yeah. So if we can do factorization, then you know the answer of this question. All right. So let's look at the factorization question. How to do factorization? Yeah. All right. Basic operation. Yeah. Here still, it's the understanding part. Yeah. In this problem-solving problem, yeah, we need to understand the problem well before we can find a solution. So understanding. We need to spend a lot of time trying to understand this problem well. Now, here, let me show. So this analysis is for the understanding. You need to do a lot of analysis work to understand this problem. Now, the basic operation here, multiplication, n equals a times b. So a is a factor of n, and b is another factor of n. So now we want to study this basic operation. And we can view, we factor this n as a product of 2 factors, a, b, product of 2 factors of yeah. That's the basic operation. So we want to study this basic operation. Try to get, because there are many cases, when you study this basic operation, there are many cases. Yeah, all right. The first case, yeah, we try to see if we can find some non-trivial factors. Here we call these AB non-trivial factors. Non-trivial factors. Right? Yeah. A is a trivial factor, and also a trivial factor. These 2 factors are trivial. We call it trivial factors, because you do not need to do anything with these 2 factors, right? That's why trivial factors. But now we are interested in non-trivial factors. Yeah. So if A and B sit in the range strictly greater than 1 and strictly less than n, and AB could be equal. Yeah. A and B could be equal. Yeah. So we are interested in the non-trivial factors for n, yeah. But sometimes you may not. If you can find non-trivial factors, that's good, right? But you may not be able to find any non-trivial factor. Yeah. If in that case, n is a prime. Yeah. If n does not have any non-trivial factor, it's a prime. Okay? If it has one non-trivial factor, it's a composite number. Okay? Yeah. That's our understanding, right? That's our understanding. Yeah. All right. Next, the main step. Now we want to determine A and B in this range between 1 and n. Exclusive. Okay? Between 1 and n, exclusive. Because non-trivial factor, so exclusive, the, two trivial factors. Yeah. All right. Question: how to resolve the uncertainty? Yeah. So here, in problem solving, actually, when you are given a general computing problem, sometimes you feel the problem is hard. Why the problem is hard? Because you need to deal with a lot of uncertainty. That's hard, right? The data given contains a lot of uncertainty. Here, uncertainty. In this range, there are so many different possibilities. That's uncertainty, right? Yeah. Too many cases. You need to consider all those cases. Yeah. So many times, if you cannot reduce the uncertainty, then it's hard. If you know how to reduce the uncertainty, make your data more and more certain, then it becomes easier and easier. Okay? Yeah. So here the question we need to study: how to reduce the uncertainty in a computing problem. Yeah. All right, so let's look at here. Yeah. In the problem solving, how to handle the uncertainty. The goal, we want to make it certain. Right? Yeah. All right. Yeah, yeah. It's not easy. Yeah. So you need to find many different properties to help you reduce the uncertainty. Okay? Yeah. Discover the properties to help you reduce the uncertainty. Yeah. Idea: reduce the uncertainty by exploring the properties. Yeah. So that's the general idea in problem solving. Okay? So very general. Yeah. So here we need to look at that. Yeah. How do we reduce the uncertainty here? Yeah. Okay? Yeah. All right. Before the uncertainty reduction, let's look at how many possibilities for our non-trivial factors. Our non-trivial factors, there are many different possibilities, right? Yeah. Yeah. So let's study those possibilities, non-trivial factors. So what property can we find for A and B here? Yeah. Yeah. If no property, yeah, because although you try very hard, right? Yeah. At this point, yeah. So most of us cannot see any property, right? So what's the property? How to see clearly, okay? At this point. Yeah. If no property, if you cannot find any property, then no uncertainty reduction, okay? No uncertainty reduction. You need to consider all the cases, okay? And you need to try all the possibilities. Because no reduction, then you need to exhaust all the possibilities. You cannot miss anyone, right? Yeah. But if you can reduce uncertainty to some level, then you don't need to exhaust all the possibilities, right? Then you can do much less work because you reduce the uncertainty. Okay? Yeah. Make it more certain, you can do less work. Yeah. So that's the point. Okay. All right. 8.3 algorithms. There is a very well-known ancient algorithm called sieve of Eratosthenes. At the break time, I use Google to look up for the pronunciation. Okay. Eratosthenes, something like that. Okay. Yeah. So So when you get home, you can try to pronounce. Yeah. Practice. Yeah. All right. So this algorithm, very old one, yeah, simple old one and very famous, yeah, sieve of Eratosthenes. Yeah. All right, let's look at this algorithm. Yeah. Yeah. So here, still, I copy the, uncertainty thing here. Yeah. All right. Still, we look at the basic operation here. Yeah. All right. And we want to reduce the uncertainty. Yeah. We try to find some properties to reduce uncertainty. Yeah. All right. But at this point, we do not have any special property. Later, we can discover some. Yeah. But at this point, we couldn't. Yeah. If not, we have to exhaust all the possibilities. Okay? Yeah? Yeah. Later in chapter 2, in module 2, I call it this method we call the brute force method. Okay? Brute force, we exhaust all the cases. That's the brute force method in our module 2 topic. Okay? Here, we need to exhaust all the possibilities. Yeah. All right. Then, let's study the range of data. The range for the non-trivial factors. Yep. AB, non-trivial factors. What's the range? Non-trivial factors. Yeah. All these numbers, right? Yeah. These consecutive numbers, 2, 3, through n minus 1. Yeah. Smallest one, 2. Yeah, because it must be greater than 1. The largest one, possible factor n minus 1, must be strictly less than n. So this is the range for the non-trivial factors. Yeah. You only need to look up the non-trivial factor in this range. Outside of this range, you don't need to waste your time, right? Yeah. Only in this range. Okay? So do the testing in this range for a non-trivial factor. Okay. All right. Yeah. Possibilities are here. Yeah. Now, yeah, because when we look at the factorization of this one, every time when you have a non-trivial factor, at the same time, you must have that B non-trivial factor, right? Yeah. Because you can do division. N over A, you get a B. Okay? So A and B, these two factors appear in a pair all the time. Every time you have an A-B pair, okay? A times B equals N. Yeah. Now we want to look at all the possibilities for A-B pair. Yeah. Now, I want to list all the possibilities of A-B pair. Okay? Now, try to exhaust all the possibilities without miss anyone. Yeah. We need to do that. Okay. All right. The first one, 2 pair, right? Yeah. Here, I'm talking about the possible pair, okay? Yeah, the possible pair. Because we need to do testing. When we list all the possibilities, then we can do the testing. Okay? Yeah, all right. Next one, 2, 3 pair, and so on, okay? Then, the first one, the first A number we fix as 2, then we go through all the numbers for B, all the possible numbers for B. as the second component. Here we have A component, B component. Two components. All right. Then, after that, then our A could be 3, right? A could be 3. Yeah. So then, 3, 3 pair. Next pair, 3, 3 pair. Yeah. Do we need to consider 3, 2 pair? No. We do not need to consider 3, 2 pair. Why we do not need to consider 3, 2 pair? Why we do not need to consider 3, 2 pair?
It's the same result from 2, 3.
Yes. Because we already consider 2, 3 pair, right? And here we assume A less than or equal to B. So we do not consider the case B less than A. Okay? In that way we can reduce the number of probabilities. Otherwise, you do some redundant work, right? Yeah. You do some redundant work. Yeah. All right. Then we keep going. Then the next round, we have these pairs. Okay? Yeah. Then we change A to 4. Then we have certain number there. All the way, the last one, A and B, both n minus 1. In this way, we list all the possibility for the AB pairs. Can you tell me how many total AB pairs? Can you count that number? Yeah, we need to count that number. How many total pairs we need to consider when we do testing? Okay, all right, let's do the calculation. Total number of pairs. Yeah, we divide it into several segments. Okay, several segments. That's the characterization, right? Let's divide it into different categories, right? Yeah. Category 1. Yeah. So this, when A equals 2, that's the first category. Yeah. How many pairs in the first category?
3.
3?
Yeah.
Oh, and you don't know the n number, right? Why? So here visually, I have dots, right?
Well, until n minus 1, until 2 reaches n minus 1 as a pair.
Yeah. For the general n, how many? In terms of n, you need to give me the number in terms of n. Not a specific number. Fixed 3, no, not a fixed number. In terms of n, how many? How many?
N minus 2.
Good, n minus 2. Can other students see n minus 2? Yeah? That's the basic counting. N minus 2. Okay? Yeah. All right. Yeah. Then, how many in the next category? The next one. The first one, n minus 2. How many? Next one. N minus what? Still n minus something. N minus what? 3. N minus 3. Next one, n minus 4, and so on. The last one, 1. Okay? Yeah. So that's the counting numbers for those categories, right? So you add them up. 1 plus summation of the consecutive numbers from 1 through n minus 2, we apply the formula, we get this formula. That's the total number of possible pairs we need to do the testing. When we check, when we want to see the non-trivial factors for n. Okay? Yeah. All right. That's the way we exhaust all the possible pairs. That's what we call the brute force method. Okay? This is the brute force method. Okay? All right. All right. Next. Yeah. So here, let's continue. There's still understanding. So here you can see how much work we need to do when we do understanding. All right, the candidate is here. Yeah, so this range, it's a set. It's a set of numbers. Yeah, that's the candidate for the non-trivial factors. Okay, all right. Yeah. Each one either prime or composite number. Because we don't have the unit number, unit 1. Other than unit 1, then each one must be either prime number or composite number. Yeah. All right. So the question, how to select all the primes in the above range? Yeah. So now we want to go through from beginning to end. The current number is a prime, we select it. If it's not prime, we drop it. Okay? Yeah. Yeah. We are interested in all the primes. The question, how to find all the primes? Another question. Part of our understanding. Part of understanding. All the primes. Okay? All right. The reason, when we do the prime factorization on n, use the primes in the above range. No? Because our goal, we want to do prime factorization. If you know all the primes in that range, when you do the testing, you can use those primes, right? Yeah. So that's the reason. So we are more interested in the prime numbers in that range. Because if we think about, if we can find the primes in that range easily, then when we do the prime, yeah, we do the testing in that range. Prime numbers in that range. Okay? Yeah. All right. Observation. The form of a composite number is, so here, because actually the prime numbers is harder to determine than the composite number. Composite number relatively easier to detect than the prime numbers. Yeah. Composite number, when you find one of the non-trivial factors, then you know it's a composite number. Yeah. Okay? But when you try to find a prime number, you need to check all the possibilities, right? Remember in our formula, previous slide, that formula, you need to check all the possibilities. After all the possibilities fail, then you can say it's a prime. When all the possibilities fail, you can say it's a prime. But when you check for the composite number, you can stop somewhere in the middle, right? Yeah. Because one of the possibilities will be successful. When you get somewhere, when you get a success somewhere, you can start immediately. You do not need to go through all the possibilities, right? Yeah. So for that reason, checking for composite numbers usually easier than checking for primes. Okay. Yeah. So let's look at the form of a composite number like this. All right. Yeah. With a range for the non-trivial factors. Because a composite number must have at least one non-trivial factor. Okay? Yeah. So we can study. Because here we assume one number n, it is a composite number, so we can assume it has at least one non-trivial factor 8, right? One non-trivial factor 8. So we can study this non-trivial factor 8. Okay, all right. Yeah. Then, we interpret the composite number n as a multiple, as a multiple of b, right? Yeah. So here, composite number, if we can write this form, n equals a times b. Now we interpret this form. Yeah. How do we interpret this form? We call it, we say it's a multiple of b, right? Yeah. Number multiple of b, some integer, some multiple of b, but that multiple number a multiple of b. Okay, that's one way to view it. And there is another way to view it, b multiple of a. Two ways to view this n factorization. Yeah. A multiple of b, b multiple of a. Okay? Yeah. So here I want to explain why this view is important. So still in problem solving. In problem solving, when we spend so much time understanding the problem, here, I want to emphasize this point. Yeah. Why we spend so much time understanding the problem? Yeah. Because we want to discover some insight. Insight. It's not easy to discover an insight. Yeah. So we need to pay a lot of hard work to find that insight. Yeah. All right. So here, still in our understanding, yeah. When we understand a problem, particular problem, many times we need to take different views. Okay? The views. You look at the same object in different views. Okay? Yeah, so here. Yeah. We need to change our views. When you change your views, sometimes if you get a good view, then you can discover the inside better. Yeah. Some views, if you have a bad view, you cannot find that insight. If you get a good view, yeah, you know, nice, good view, then you can find that insight. So that's why we need to take different views. We try to find the insight. Okay, all right. So here, the view. Yeah. This is a view. Okay. A multiple of b. N is a multiple of b, composite number. Also b multiple of a. No. All right. So this view would result in that well-known algorithm sieve of Aristotelian algorithm. Aristotelian algorithm. Whatever, yeah. My pronunciation may not be, you know, I need to practice more. Okay? So this view will result in that algorithm, sieve. Okay? Yeah? All right. Yeah. The property. It is easier to determine a composite number than a prime number. That's another property we can use in this sieve of Aristotelian algorithm. Aristotelian algorithm. Okay? Yeah. This property. All right. Now, after this preparation, now we are ready. I need to keep track of the, oh, sorry. Oh, yeah, just let me know. Yeah, because I feel I have enough time, but you know, I forgot. Then I saw some students, you know, some actions. Now I guess I may pass the time. Sorry, yeah. And next time I put a clock in front of me. Yeah, that is much easier because in the classroom I couldn't find any clock. Yeah, usually in other classroom I always have a clock so I can see. Yeah, for this classroom, no clock. Yeah. Yeah. Next time I will bring a small clock, put it here, so I won't miss. Yeah. Yeah. Just let me know. Okay. Yeah. All right. Sorry. Yeah.